Hello, I forget exactly which video I was watching. I think it might have been a debate on some Discord server somewhere. I got the idea to look up online a table that is easily verifiable, supposedly showing the maximum distance visible based on observer height, and I came across this PDF. It is table 12, the distance of the horizon, from the nautical almanac.com. I used an app on my phone that allows me to take a picture and it's going to look for text and convert the image to text. So I created this spreadsheet. There's the URL, by the way. I'm probably going to share this spreadsheet, so look in the description below for a copy. The original worksheet is a direct copy of what my phone has extracted. And then I had to take this and copy it over here. So it goes as far as the full 820 feet above mean sea level, I guess. So the point of this exercise was to be able to see if I could use the well-established and published maximum visible distance as expressed in statute miles. I converted the statute miles to meters in this case so that I could use the height in meters with the distance visible in meters and to see if I could calculate a radius. Flat Earth basically comes down to arguing over whether the Earth is a sphere or whether the Earth is flat, like a pizza. So if we pretend that the Earth is spherical for now, how can we calculate the radius of the Earth based on those visible distances and those observed heights? It's very plain to see that the higher you go, the further the distance that is visible. So in this model, if I'm standing at the intersection of these two lines looking off to the right, my sight line is this tangent line, and my plumb line and the plumb line of this maximum visible distance should both intersect somewhere in the middle of the Earth over here. And if you pay attention, by gaining some observer height, you should be able to see a little bit further. By gaining a little bit more height, you should be able to see a little further still. And so we can look at this as a right angle triangle where the adjacent is the radius of the Earth. The hypotenuse is also the radius of the Earth, but it also has an extra little bit. And the distance between the observer and the maximum visible distance would be the equivalent of the opposite side. We can then apply the formula side C squared equals side A squared plus side B squared. Side C, which is the hypotenuse, can be represented as the same length of side A plus an extra height. So if we substitute C for A plus H, this is what we get. I multiply the left side out. I've got A squared plus AH plus another AH plus H squared equals my other side. I can combine these AH's to form 2AH. Now I've got A squared on both sides. I can eliminate that A squared. Now I'm left with 2AH plus H squared equals B squared. I can subtract H squared from both sides. I've got 2AH equals B squared minus H squared. And now I can divide both sides by 2H, which leaves me with A. So I've now derived the formula to calculate the radius of the Earth simply based on the square of the maximum visible distance to the horizon in statute miles, or converted to meters. I square that minus the square of the observer height that I will also use in meters, and then I divide that by 2 times my observer height in meters, and that should give me the radius of the Earth in meters. And that is this formula right here. And before flat earthers cry foul that I'm just presuming a globe, let's consider the other possibility that the earth is flat. So we have our plumb line would be the equivalent of the opposite side. The length of the opposite side would be our observer height above mean sea level. The adjacent A would be a flat and horizontal line that is parallel to mean sea level. And the hypotenuse would be the sight line that you would see from your observer height to the maximum distance visible. So theoretically, in an ideal flatland world problem, the area of green is theoretically visible, and anything to the right of this green line is unresolvable for some magical reason, which some flat earthers will say is due to the Rayleigh criterion, that our eye cannot resolve that due to reasons, etc. So, for example, this angle here that you can see right up if you look straight down is a much greater angle than this angle way out over here, this angle here being a much smaller angle. And then somewhere right around here would be the maximum visible distance according to flat earthers, so that this angle is resolvable and you can see up to this distance, and this angle, which is a slightly smaller angle, is now just past the Rayleigh criterion and things just magically disappear. At least that is the way I understand it. So if that is the case, we can apply straight basic trigonometry. Opposite side B divided by the hypotenuse side C is equivalent to the sine of this angle theta. If we take the arc sine of both, arc sine cancels out sine, so we are left with this angle theta equals the arc sine of observer height B divided by this distance to the horizon, hypotenuse side C. And that's what I did in column N over here. And so now we get to see what the results are. I created this chart. The blue line represents this calculated radius R here. I copied the average radius into column J, and I made that as an extra data set so you can see what the ideal radius is regardless of your observer height. And it seems to track computed radius fairly well. There is quite a bit of noise because they've only resolved in their table to 1 or 2 decimal places. The red line, however, is this vanishing distance angle column, and you can see that there is no easily discernible correlation between the observer's height and this vanishing distance angle. So a good question to ask flat earthers is, if this table is accurate, and I have no reason to doubt its accuracy, otherwise it would not be published in the Nautical Almanac, then why, deriving a very, very simple formula, can I calculate a radius of the Earth that, if I also solve this equation for k right here, I get the same refraction coefficient, for example, that is referenced in Walter Bisland's Earth curve calculator. So that's going to be it for now. Thank you for watching. If you liked the video, I would appreciate the thumbs up, the subscribe, comment below, all that other good YouTube stuff. And I'm going to see you again in another video at some point before too long. Bye for now.